Hello guys, today I would like to continue my study of simulation in Ansys Fluent around the airfoil. So I would like to set up my boundary conditions first. I will select my edges on the bound of my control volume and I will name them as inlet. Okay, now I will select the edges on the outlet and I will name them as well. In the center of my simulation I have the airfoil. I'm selecting here 4 edges and will name them as a wall. That's it. Now, please do not forget to check this option of the design modeler, graphics, and facet quality. It must be equal to 10. If it's lower, please change to 10 and update your geometry. Otherwise, you can lose some details in your simulation. Well, I set my options and now I'm ready to continue my simulation. I will update my mesh to Fluent, select parallel processing, all the other options by default, and now we are able to see classical window of the Fluent. Now I will set up all the options one by one, starting from the general options. They are the density-based model, steady simulation, planar, absolute velocity formulation. In the model, I will select inviscid flow. In the materials, air with a constant density, so my flow is incompressible. In the boundary conditions, I have to set up inlet. It's already defined as the velocity inlet. And here I will put the value. My velocity on all the inlet face will be directed with the velocity magnitude of 44 meters per second. This corresponds to 300,000 Reynolds number. And my velocity direction will be set according to the coordinates of the identity vector. So I would like to calculate my flow for 4 degrees of the angle of attack. I will calculate the sine, Control C. This would be the y component of the flow direction, and cosine. Okay. Now we also have to set up the pressure outlet. On the outlet part of our control volume, flow will exit with some direction. It will be the same direction as the inlet. So I have to set up all the options same. Okay, now my inlet and outlet are well defined. My interior by default is interior, and the surface body is also inside. The wall is the wall by default. Then I will have to set up the reference values. Reference values are used to calculate aerodynamic coefficients. So my area is 0.1 meter, density is set, the length is also 0.1 meter, the velocity is 44 meters per second. Okay, now I have to set the methods. Methods are implicit, ROI, least square cell based, second order upwind, high order thermal relaxation. In the controls, I will put current 1. After some simulation will be performed, I will increase the current number. Now I will define the report definitions. I would like to see my values of the forces, a lift force coefficient actually, on the wall, on the y direction. Actually, this will be not the lift force coefficient, it will be normal force coefficient. So I will name it as Cn and click OK. This value I also will output after in the console to see it on every cycle. Okay. In the monitors, we'll have to check parameters. In the report plots, we will define also our Cn. I will add here and print to console. Okay, so now we will be able to see this value of the normal force coefficient. In the initialization part, I will select the standard initialization from inlet. Automatically parameters appear below and initialize. After doing this, I'm able to define the graphics contours. I would like to visualize my pressure contours inside. Okay. And here I will select my zone of interest for visualization. I would like to see all my distribution of pressure around airfoil. Now I will save my view. Click on front, save. OK, and set as default as well. And close. So when we display it again, it appears in the same view. Close. So we are able to see now this contour below. Second parameter I would like to see is two-dimensional plot of my pressure coefficient. Pressure coefficient on the wall. Plot. By default it's 0 since we didn't start simulation yet. And close. So now this pressure coefficient plot is also available. Now I would like to set up some solution animations to see distribution of flow properties during the simulation. I will visualize flow properties every 20 iterations. I will save them in the memory. One will be contour of pressure. Okay. it appeared here as animation 1, and the second one will be my pressure coefficient. It appears here as well every 20 iterations, and OK. So we have two animations created. Now I am able to run my simulation. To do so, I will run first 100 iterations just to start my flow, update every 20 iterations, and then after I will change my current number from 1 to 3 to calculate faster. We see change of the coefficient, of the lift coefficient. Okay, started to appear pressure coefficient and the contours of pressure. Okay. Well, after some flow established, we can see drop of the residuals, and I would like to adjust a bit my options. Well, here the main one is the control. I change the current number from 1 to 3, so my simulation will converge much faster. Now I will go to run my simulation for 2000 cycles and calculate. So it will take some time. I will put to pause this video, and when it's finished I will continue. Okay, after a few minutes this solution was converged. We can observe that it happened during approximately 1100 iterations. We can observe distribution of the pressure and the pressure coefficient. Actually, the value of pressure coefficient is quite close to the classical and experimental pressure coefficient distribution. Here we also can see the lift coefficient value, which is approximately 0.44989. This value of the lift coefficient is not the lift, but the normal coefficient. But since our angle of attack is very small, equal to 4 degrees, this is approximately equal to the lift coefficient. Once we compare it with the this numerical value with experimental, we will find that the difference between experimental and numerical value is smaller than 1%. So our simulation was successful in terms of the lift coefficient. Now we are able to build visualization of this data. This simulation can show us more parameters than just thermodynamic properties. I will go to return it to the front view. Okay, and here we are able to produce another values. Very important parameters are the velocity, magnitude, for example. Here we can see it well, and also vectors of the flow. which by default cannot be visualized really nice, so we have to adjust the options. I will try to skip some vectors around. Now they are quite big, so I will probably reduce their size. Okay, and reduce their quantity. And draw also the wall of my airfoil like this, so we can see same time direction of the flow, value of the velocity, and the wall. Okay, we also are able to visualize the direction of the flow like a path lines. For this, several options are available. If we will, for example, start our path lines from the inlet, we are able to see the general direction of the flow inside our control volume. But unfortunately, in these path lines we do not see our airfoil. It's somewhere in the middle and very small. So here we see some small disturbance of the flow, but we do not see the airfoil by itself. I would like to draw it again and show my streamlines. So here in this region, actually, I'm interested to see my streamlines. To make it possible, I will create a new surface, new line. I will define it with the mouse in front of my airfoil, somehow like this. By these 2 points, I will have this line in between. I create this line, will have name 6, and close. Now I can start my visualization from this line, and we can see very nicely visualized streamlines around the airfoil. I can change the values, for example, to pressure, and same time I will be able to see pressure distribution and the direction of the flow. Okay. Very nicely. If you want to get the values of the forces and moments, you always can go to Reports, Forces, and find these values here. Forces near the wall. On X direction, it will be our value of the drag. Okay, it's negative here because of direction of my axis. And if you want to find the lift, it will be the value of the lift force. We can see it's only pressure force. There is no viscous force because my flow is inviscid. Okay. We also can visualize another parameters like moments and center of pressure position. Fine. So after we execute this simulation for 4 degrees angle of attack, and it starts to work well when we compare it with experimental data, we have set this project, this default project, and now we are able to go to the next step and share this project for different values of attack and collect this data for various angles of attack and produce our report. Okay, so how to make it? I will save my project first. I will use these changes for all the calculations. I will exit my Fluent. Okay. And now I'm able to produce the children processes. I go to Component System. I want just Fluent without meshing. I put here, and I will select my mesh and transfer here. This I will name, for example, 0 degrees simulation. I also can do it for another angles of attack. I will create another Fluent. And I will transfer it here. And I will call it, for example, 8 degrees angle of attack. And same I can repeat for all the angles which I would like to check, from minimal one to maximum angle of attack where I have my flow separation. Thank you for watching.